All right, hello and welcome. Today, we're putting on our detective hats because we are investigating one of the biggest questions in all of science. We're going to follow the clues, the breadcrumbs that generations of scientists have uncovered to piece together the story of life itself. Okay, let's dive right in. So, what's the central mystery we're trying to solve? It's this. You look around the planet and see everything from the tiniest microbe to the most massive blue whale. How did all of this incredible variety of life come to be? How are we all connected? I mean, it's a massive puzzle that goes back billions of years. And, like any good detective story, you can't solve it with just a single piece of evidence. No way. Instead, we have to look for clues hidden all around us, in the bodies of living animals, buried deep within the earth, and even in the ideas of thinkers from long ago. Okay, our first stop in this investigation is going to take us to the anatomy lab. We're looking for clues in the very structure, the very blueprint of living things. This is where it gets really interesting. By comparing the anatomy of different creatures, you can find these, startling similarities in their underlying designs. These similarities are kind of like a family resemblance, and they're a huge hint that there's a shared history there. And this leads us to an absolutely crucial piece of evidence, the concept of homologous organs. So think about it like this. Imagine a single ancient toolkit that was inherited by a bunch of different descendants. Now, over millions of years, one descendant shapes a tool for grasping, another shapes it for swimming, and another one for flying. But the underlying blueprint, the core design of that original tool, is still visibly similar. That's homology. And this slide just illustrates the point perfectly. Over on the left, you've got a human arm and a whale flipper. They look pretty different, and they do totally different things. One grabs, the other swims. But inside, they share the exact same bone structure. That's homology, and it points directly to a common ancestor. Now look on the right, a bird's wing and an insect's wing. They both do the same job, flying, but their internal structure is completely different. That's what we call analogy, and it tells us they just evolved flight independently. So remember, it's the shared structure, not just the function, that whispers the secrets of a common ancestor. All right, we're leaving the lab. Our investigation now takes us out into the field to uncover secrets that are buried in the rock right beneath our feet. Fossils are basically our time machines. They are the hard physical proof, literal snapshots from history, that creatures very, very different from us once roamed the earth. And it's more than just bones. Fossils can show us entire extinct ecosystems and give us this undeniable record of change through deep, deep time. So, the first rule of this geological detective work is actually really simple. Rock forms in layers over time, right? Well, that means the fossils you find in the deeper, lower layers are almost always older than the ones you find closer to the surface. It gives us a basic timeline. But we can get even more precise than that. A lot more. By measuring the decay of radioactive elements trapped in rock, scientists basically have a geological clock. And this isn't just about giving a fossil a birthday. It lets us build an exact, verifiable timeline. We can pinpoint when major groups of animals appeared, we can track the rate of evolutionary change, and we can confirm that simpler life forms consistently show up in the record before more complex ones. Okay, so let's recap. The evidence is pretty clear. Life changes over time. The anatomical clues and the fossil record, they demand an explanation. They demand a mechanism. And that brings us to our first major suspect in this detective story, Jean-Baptiste Lamarck, who offered the very first comprehensive theory for how it all might have happened. Now, you have to realize, Lamarck's core idea was revolutionary. He was living in a time when most people just believed that species were fixed and unchanging, period. But he looked at the evidence and dared to argue that no, they could and did evolve. He saw the clues and he proposed a reason for it. So here was his proposed mechanism, the theory of inheritance of acquired characters. Put simply, he believed that any traits an organism develops during its own lifetime, through effort or just not using something, could be passed directly to its offspring. So if you work out and get strong, your kids will be born stronger. It's a really intuitive use it or lose it model of how things are passed down. And the classic example everyone uses to explain this is the giraffe. So in the Lamarckian story, you start with short-necked ancestors who are always stretching to reach leaves on tall trees. He thought this constant effort actually caused their necks to get a little bit longer within their own lifetime. And then, and this is the key part, they passed that newly acquired longer neck on to the next generation. It's a simple and, you have to admit, a pretty compelling story. It's an elegant idea for sure, but in a detective story, you have to test your theories against the hard evidence. So let's put Lamarck's theory on the stand and see how it holds up. It was a groundbreaking hypothesis, no doubt about it. But does it actually match reality? When we look at the world around us, do we see this mechanism in action? Well, the key counter-argument came from a scientist named August Weismann. He pointed out that there's a fundamental difference between the cells that make up our bodies, our muscles, our skin, our somatic cells, and the reproductive cells that we pass on, our germ cells, like sperm and eggs. Changes to your muscles, in theory, just shouldn't alter the genetic information that you pass to your children. And the real-world evidence against this idea is just overwhelming. I mean, think about it. People have pierced their ears for thousands of years, yet babies are not born with holes in their ears. A blacksmith develops incredibly strong arms, but their children aren't born with powerful muscles. And in a rather conclusive, if a little grim, experiment, Weismann himself cut the tails off of rats for over 80 generations, and not a single one was ever born tailless. The acquired characteristic just wasn't passed on. So the verdict is in. While Lamarck was absolutely right that life evolves, his proposed mechanism, the inheritance of acquired traits, was just incorrect. It was a fascinating first draft, a really important step, but the evidence just didn't support it. The case went cold. And this leaves us with a final massive question. The clues from anatomy and the fossil record are still there. The evidence for evolution is undeniable. So if Lamarck's use it or lose it idea isn't the answer, then what is? The mystery of how life evolves was still waiting for its master detective.